In this video, you're going to learn about sequences. First, we're going to define them, and then we're going to talk about how we can find terms of a sequence and apply them in some realistic problems. So let's start off with what in the world is a sequence. So a sequence, first of all, is a function whose domain and if you recall, a domain is the set of inputs, right? This is what you're allowed to plug into a function. So it's a domain whose inputs is the set of consecutive integers. So those consecutive integers, of course, we're going to start with 1, 2, 3, 4, so on and so on and so forth. So to show that these inputs go on, we use the ... to indicate that we can plug in all of the integers starting with 1 and going on infinitely long. If that's the case, if the domain does have those dots, then this is going to be an infinite sequence because the domain is infinitely long. However, let's say that the domain for a sequence is the following. Let's say it's 1, 2, 3, and 4. If the domain is just those 4 values, then that would be a finite sequence because it has a limited number of terms. Now, the domain is the set of those consecutive integers. The range of a sequence is called the terms of a sequence. So the range, remember, is also the outputs, right? So you plug in one of the integers from the domain and you get out a term of the sequence. So here's just maybe a little bit more of an organized way to look at this. If you have a domain of the following, these are of course your inputs of 1, 2, 3, 4, so on and so forth, until we just plug in any integer n, the range or the terms of the sequence would be called the following. If you plug in 1, the range is called a sub 1. If you plug in 2, that term or that output is called a sub 2. If you plug in 3, you get a sub 3, 4, a sub 4, and so on. If you plug in n, we call that term or that output a sub n. So one of the first things that I'd like you to be able to do, and you're going to see this when you practice in your homework in class, is I want you to write the first 4 terms of the sequence. So let's do that. Let's write the first 4 terms of the sequence. And we'll define the sequence in 2 ways. In part A, I'm going to call the sequence a sub n and define it as 2 times n. So, if that's my sequence, the first term we'd find by plugging in n equal to 1, because that's our first number in the domain. And so that would be a sub 1 equal to 2 times 1, which is 2. In other words, the first term, a sub 1 equals 2. When we plug in 1, we get out 2. The second term, we would let n be equal to 2. So, to find that, that would be a sub 2. That would be 2 times the input of 2, and we would get out 4. The third term would be n equals 3. That would be a sub 3 equals 2 times 3, or the term 6. And let's end with the fourth term of the sequence. That would be when n equals 4. That would be a sub 4 for the fourth term, and that would be equal to 2 times the input 4 for an output of 8. Those would be the first four terms right here, 2, 4, 6, and 8. In other words, the evens there. Now, part B, I'm going to define another sequence in a little bit different way. Let's call this one f of n instead of a sub n. I'm going to use f of n. And let's call this one negative 4 to the power n. Okay, so the first term would just be when n equals 1. So that would be f of 1. We're plugging in 1, and we would get negative 4 to the 1, which is just negative 4. The second term would be when n equals 2. That would be when we plug in 2, we would get f of 2. And so we'd have to take negative 4 and square it. Now, since the negative's in parentheses, it's really the product of negative 4 and negative 4, giving us positive 16 for that second term. The third term would be when n equals 3. This would be when we do f of 3. That would be negative 4 to the third power. When you have a negative to an odd power, that would be a negative output. That would be negative 64. And the final term we'll do is the fourth term when n equals 4. This would be f of 4, or negative 4 to the fourth. Now, a negative to an even power is always going to be positive. I think that's going to be positive 256. So that's the first type of example I would like you to be able to do starting tomorrow in classes. If I give you a sequence, please write out the first few terms of that sequence. Now, sometimes you can write a rule of a sequence if you see a pattern. So let's go to example 2 here. What I'd like you to do for example 2 is describe the pattern, of the sequence if you notice it, and then write the next term of the sequence. And then lastly, write a rule for the sequence. So let's do two of them. For part A, I'm going to give you the following terms. Let's say the first one is 3, then I get 6, then 9, then 12, etc., etc., etc. We have to try to figure out how is this sequence being generated. Now, a good place to start when you're trying to wrap your head around this is trying to see if there's a relationship between the inputs, or your domain values, right, and the term. So in order to get 3, we did something to the number 1 to get 3. And then we plug in 2, and we do something to get 6. And we plug in 3, and we get 9. We plug in 4, and we get 12. So we have to think, what are we doing to the input each time to get the output? Now this one, it's a little bit clearer that every time here, we multiply the input by 3 in order to get the output, or the term of the sequence. So if I had to describe the pattern, we are just multiplying inputs by 3. So the next term, if I had to answer the question, the next term of the sequence would just be 5 times 3 to get 15. That would be the next term. Now, the last part is to see if you can write a rule for the nth term of the sequence. So what is a sub n equal to? Well, since it's just 3 times whatever the input is, you can just say it's 3n. That's it. So that's it for part A. Let's do one that's a tiny bit more tricky. Let's say these are your terms: 1, 8, 27, and 64, etc., etc., etc. Now, what are we doing to 1 to get 1? I'm not really sure. What are we doing to 2 to get 8? Maybe multiplying by 2. but if I take 3 and just multiply by 2, I'm not going to get 27. So it's not just multiplying by 2. If you think about it, it looks like what we could do, the relationship between 2 and 8 and 3 and 27 and 4 and 64, those are all the cubes of the inputs. So I think if I had to answer or describe the pattern here, I think we are just cubing the input. So the next term would be 5 to the third, which I believe is 125, would be the next term of the sequence. The general rule for the nth term would just be whatever n is to the third power, and that would be the rule for this guy. I'll be nice, I'll do one more with you, because some of these can be a little tricky. So what if I give you this one? 0, 2, 6, 12, etc., etc., etc. So we have to think of, what are we doing to 1 to get 0? What happens to 2 to get 2? 3 to get 6, 4 to get 12. Well, it's not very clear. It looks like 1 to get 0, we might be multiplying by 0, but clearly we're not multiplying 2 by 0 to get 2. Let's just see if we can think of this. So 1 times 0 gives me that one. 2 times 1 gives me 2. And doesn't 3 times 2 give me 6? And 4 times 3 give me 12. It looks like for each one of these terms, right, 0, 2, 6, and 12, I'm multiplying the input by 1 less than the input. So like if the input's 1, I'm multiplying by 0. If the input's 2, I'm multiplying by 1. If the input's 3, I'm multiplying by 2. If the input's 4, I'm multiplying by 3. So it looks like, to describe the pattern, I'm multiplying the input by 1 integer less than the input. So for example, the next term, which is going to be 5, I'd have to multiply by the number 1 less than 5, which would be 4. So I believe the next term would be 20. So how do we write the rule for that? What is a sub n? Well, if that's the nth term, we multiply by 1 less than n, so that number can be written just as n minus 1. And if you think about it, that makes sense. If I plug in 1, I would have to multiply by 1 minus 1, so it's 1 times 0, that gives me the output of 0, which kind of matches. And I think if you check the other terms, that would work. That's a little bit tricky, and I think it takes a little getting used to and a little bit of struggling, so to speak, to get good at these. There's one more example I'd like you to try, and it's the following. So I'm looking at example 3 from our textbook, which is kind of a cool problem. You're working at a grocery store and stacking apples in the shape of a square pyramid that has 7 layers. And they're calling the first layer that top row, or that top layer with 1 apple, and that second layer the one that looks like it has 4 apples, and this one is the third layer, and then of course the bottom one being the 7th layer of apples. What we want to try to do is write a rule for the number of apples that are in each layer and then graph the sequence. Well, I think it's a good idea. If we're going to try to write a rule, we can try to make this into a problem like what we were just looking at. So let's call n the row or the layer of apples. Oops. And then a sub n is just the number of apples in that layer. The layer, if I can spell layer. So let's see if we can make a quick table. So if I have n and a sub n, so if n is 1, that's like the top layer, it looks like we have 1 apple in that layer. If n is 2, if we are in the second layer, it looks like there's a total of 4 apples there. If we're in the third row, it looks like it's 3 here by 3, so that 3 times 3 is 9. If we had to do the fourth row, you can see there's 1, 2, 3, 4 apples, and 1, 2, 3, 4 apples deep. Hopefully you see the pattern here. For each n, what are we doing to n to get a sub n? Or for each layer, what are we doing with that layer number to get the number of apples? Hopefully what you're saying is we're squaring it, right? If you square 1, you get 1. You square 2, you get 4. Square 3, you get 9, and so on and so forth. So we could define a sub n to be whatever the layer is, n squared. And that will be our rule. So we can use this now to make a graph. And we're just going to maybe graph the first few values. So you kind of get how you can graph a sequence. It's a little bit different from graphing a function, but not much. We would still call the input the x-axis. In this case, the inputs are n values. The output is a sub n, which is n squared, right? N squared up there. Let me rewrite that so it doesn't look confusing. So this is n squared, and this is 0. Let's let that be 1, 2, 3, 4, 5, 6, 7. And our outputs, I'm going to maybe count by 2s here because they grow pretty quickly. So if I count by 2s, this is 0, 2, 4, 6, 8, 10, 12, 14, 16, 18. So if I plug in 1, I get an output of 1 apple, which would be right about there. If I plug in 2, I get 4. 3 would give me an output of 9. 4 would give me an output of 16. 5 would be 25, which is even higher. So this is what the graph of the sequence would look like. By the way, I want you to think about why you would not want to do this. And maybe think of why you wouldn't want to do that. If you can come up with that answer, tomorrow might earn you a couple stamps for why you would not want to connect the dots with a curve when we're graphing a sequence. So don't do that. Let's leave it like that. To finish off, guys, I have a few problems that I would like you to try on your own with your group before you can start practicing, and here they are in just a moment. So for the first one, write the first 6 terms of each of the sequences that I gave you for part A and for part B. For number 2, see if you can describe the pattern, write the next term, and give a rule for the nth term of the given sequence. Good luck, thanks for watching, and we'll see you guys tomorrow.